Hey everybody, welcome to the thingy. I'm just gonna see. It says the stream health is healthy. Let's go. I think I figured out this weekend why the stream might be so weird. I think we're having router problems with the whole computer, with the internet between my computer and the internet. So if those router problems have been solved, I was trying to podcast this weekend. It didn't work. If those router problems have been solved, then maybe this will be easy. I don't know. Okay, so hello, welcome. It's time to start the stream, and 0 people are watching. Well, anyway, let's do these questions. There's some from chapter 1, some from chapter 2. There was supposed to be an assignment due on Wednesday, but then I remembered that I'd forgotten to tell you about it because of the book drama. How long it took for everybody to get onto mastering physics. We are kind of behind on assignments, so there was going to be a double assignment this week. One due on Wednesday, one due on Friday. They're not very hard, but I've bumped the one due on Wednesday to be due on Friday, so you have a little bit more time. Okay. So anyway. Let's start. First one, turn to page 27 of your book. This is question 32. And let's start. The question goes like this. A ball on a porch rolls 60 centimeters to the porch's edge, drops 80 centimeters from the porch's edge. Wait, no. Drops 40 centimeters, continues rolling on the grass, eventually stops 80 centimeters from the porch's edge. What's the magnitude of the ball's net displacement in centimeters? How do we tackle this question? The question isn't asking what does the ball's tachometer say? It's not how far did the ball roll. It's how far from the initial position is the ball. So let's draw a little sketch of what this looks like. So here's a porch. Your ball starts here, and then it moves, let's see, it moves 60 centimeters to the porch's edge. So there, that's 60 centimeters. And then it goes down 40 centimeters. You know what? I should try using the, oh no, what's going on? I should try using this graph paper, because it's pretty cool. So in class this week we've been doing vectors, and this is a very vectory problem, literally. So let's try drawing it on the graph paper, because vectors are essentially arrows on graph paper. Okay, so it goes 60 centimeters to the porch's edge. Oh no. Okay. 1, 2, 3, 4, 5, 6. And then it goes down 40 centimeters. 1, 2, 3, 4. And then it goes 80 centimeters. 1, 2, 3, 4. No, that's 3, 4, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Good. 80, 40. So, like I said, the question's not asking for how far the ball rolled. The ball rolled 180 centimeters. The question is, how far is it from my initial point to this final point? This is a question you can do quite easily with vectors. I mean, as you see, I've drawn everything with vectors. But, you know, I don't think we've reached the point where we can talk all that easily about vectors. So what we're going to do is we're going to draw a big rectangle around the red vector that I'm supposed to calculate. So this triangle, this is a rectangle, but there is a hypotenuse. The red line's the hypotenuse. That's what we're trying to find. And each of these sides, we can figure out their length. This is 40. So this side's 60 and this part's 80. So the total on this side is going to be 140. And so the length of the hypotenuse, according to Pythagoras, is 40 squared plus 140 all squared. I'm going to get my calculator out, do this question. 40 times 40 plus 140 all squared, square root that, 145.6 centimeters. Okay, next question. Next question is question 35. Do it as quickly as I can. Billy drops a watermelon. That's not good, Billy. From the top of a 3-story building. That's terrible. Somebody's going to get hurt 10 meters above the sidewalk. How fast is a watermelon going when it hits? All right, so let's draw a little diagram. There's Billy before you ended up in jail. There's the watermelon, and it goes down. Oh, geez, what is this? It goes down, and it hits the ground. So the question is, how fast is it traveling? So what we're going to do is ask ourselves, what do we know about this particular question? This is a constant acceleration question. So let's make note of some things that we know about this. We know that this is 10 meters tall. You know that the acceleration is going to be downwards. That's not the velocity, that's the acceleration. And it's going to be 9.81 meters per second squared. Okay, so to go any further in this question, I need to design a coordinate system, a reference frame. So I need to decide where the origin is. Where should I make the origin? Nobody's saying anything in the live chat, so I'm going to make the origin exactly halfway down. That's where my origin is. And I'm going to make down increasing. Why am I doing it that way? Because I can do whatever the dang heck I want. So this, the ground, is at +5, and the top here is going to be at -5. So, to do a constant acceleration question, we're probably going to rely on the constant acceleration equations. How do we do that? We need to know what these values are. So the initial position is going to be -5 meters because it's up here. The initial velocity, the implication is that it's 0. Why is that implied? They don't tell us what they do, and they say Billy drops a watermelon. The implication when something drops something is that the initial velocity is 0. And the acceleration is 9.81 meters per second squared. Is it positive or negative? The direction of the acceleration is in the same direction as increasing, so it's positive. So I'm going to plug these into my equations. X is equal to -5 plus 0t minus 9.81 over 2t squared. And v is equal to 0 minus 9.81 times t. I'm going to erase some things here just so that I can make my life easy. Okay, so the question's asking me what the velocity is. It's asking me about the speed, right? How fast? That's a speed question. And so to figure out the velocity, I need to know the time it hits the ground. And so to do that, I need to use the only clue I have, which is where the ground is. X ground is at +5. So 5 is equal to -5 minus 9.81 over 2t squared. I guess I'm calling it ground now, not hits. Okay, so I just need to solve this equation. How am I going to do it? First rearrange. 10. Then isolate. 2 over 9.81. Wait, this is supposed to be plus. Plus. All that talk about how going down is the positive direction. Okay, so that's going to be giving me t squared. So t ground is equal to 10 times 2 divided by 9.81. I'm going to take the square root of that. 1.43 seconds. And so to find the velocity, oh wait, that's supposed to be plus as well. 9.81 times 1.43. 14.0 meters per second. That's how fast he's going. All right. Any questions? We'll stop for a second or two and see if anybody has any questions to ask in the live chat. In the meantime, I'm going to turn to page 68 to start the next question. So that's chapter 2. 68. There's lots of questions here. All right. So has anybody got any questions? No, the screen has caught up with me and there are still no questions. So let's move on to the next one. Next question, page 68, question 9. Oh, 68's on question 67. 9 goes like this. A bicyclist has the position versus time graph shown in, and then it shows a picture. What's the bicyclist's velocity at 10 seconds and at 25 seconds and at 30 seconds? Okay, so I'm going to try to sketch the graph here as best I can. 1, 2, 3, 4. Okay, so it goes up 1, 2, 3, 4. That's x. So that's 100. There's 50. That's 0. And 10, 20, 30, 40. T in seconds. And here's what the graph looks like to the best of my abilities. It starts here, and in 20 seconds it makes it up to 100. And it stays at 100 for 1 second. And then in the next one it comes all the way down like that. So we're asked about the velocity at different times. At time 10 seconds, at time 25 seconds, and at time 35 seconds. And so the thing we're looking for is the slope of these graphs. All right, so t is equal to 10. Let's draw that. Horizontal displacement here is 20, and the vertical displacement there is plus 50. So v is equal to plus 50 over 20. So that is 2.5 meters per second. And at time t is equal to 25, that's a horizontal line, so the slope is 0. And at t is equal to 35 seconds, that's this one. So the horizontal displacement is 10 seconds. And the vertical displacements on this, the change in height is minus 100. So it's minus 10 meters per second. Okay. That's pretty fun, right? I had fun, you had fun, everybody had fun. Next question, question 17. Question 17 goes like this. Picture 2.17 shows the position graph of a particle. Draw the particle's velocity as a function of time. Does this particle have a turning point? If so, what time or times? Oh. Huh. That's a fun question. Alright, so let's try drawing the graph. Okay, so that's 20, and that's 10, and that's 1, 2, 3, 4, t, x, 1, 2, 3, 4. So the graph looks like this. It starts out like this for 1, and then it goes up to 20, and then it goes down like that. Let's draw the V versus T diagram. Again, the thing we're interested in is the slope at all these times. So you could argue that, hold on, I guess I'll do it in yellow. We can divide up this graph into regions where it has constant slope, luckily. So for the first time, the slope, it's horizontal, so the slope is 0. For the second time, the displacement, let's see, I'll do it in green again. You go across by 1 second and you go up by plus 20, so it's 20 over 1. And for this time, you go across 2 seconds and you go down 20. So this is 20 meters per second, and this is minus 10 meters per second. So it's in meters per second, minus 10, minus 20. So you start off with 0 velocity, as we said before, and then you go up to 20, like that, for that time period, and then you go to minus 10 this time period. Okay, so the next question, question B, says, does the particle have turning points? If so, what time? And if you took physics 11, maybe you didn't quite understand it, the thing you're going to look for is V is equal to 0. And if you're dealing with instantaneous velocity, this is often the places where there are turning points. But geometrically speaking, like speaking in terms of like motion, a turning point's where you turn around, where your velocity goes from positive to negative. So I don't think I'd describe this part here as a turning point. The slope does change, but I'm not sure if I'd say you turn around. This point you definitely turn around. First you're going in the positive direction, then you're going in the negative direction. So I'm going to guess the answer is T is equal to 2. Maybe you get this as a mastering physics question. You can see what the textbook writers say, but you know, language is pretty ambiguous. Next question, question 21. 21 goes like this. Figure 2.21 shows the velocity graph of a bicycle. Draw the acceleration graph. Give both axes at approximate numerical scale. Okay, so in this one, you're probably going to be asked to graph something using mastering physics. Let me just, I'll do my best. I want you to note something too, and that's that we're playing kind of fast and loose with the scalings on the sides of the graphs. This is T in seconds. This is in tens of seconds. So 2 squares this way means 1 second. 2 squares this means 10 meters. This one's even worse. 1 square means 10 seconds, and 2 squares means 50 seconds. I'm just telling you this because you should be aware when you see a graph what kind of units and increments they're using, because you can see a pretty nice graph and completely misinterpret it if you're not careful. Okay, so we'll call this 2. So this is in meters per second, and this one's 4. That's 2 seconds, and that's 4 seconds. This graph looks like 4 to 2. So it looks like this first, and then it looks like that. So on these graphs, drawing the acceleration as a function of time is a lot like us drawing the average velocity in the previous examples. So just like before, we can split this up into regions where there's a constant slope So the slope on the v versus t diagram means that there's a constant acceleration. Okay, so let's do the calculation. For the first one, hold on. For this one, you go across by 2, and you go down by 2. So delta v is equal to minus 2. Delta t is equal to 2. So minus 1 meter per second squared. And on the second one, delta v is equal to 0. Your velocity doesn't change, and so the acceleration is going to be 0. So this graph is going to look like it's going to look like first you're accelerating at minus 1 for a while, and then you go to 0, like that. Next question is question 27. Oh, cool. This book has lots of biophysics questions, and I like them because they're fun. So there's a fish called a pike. Pikes look like this. They're long. You got your back fins and your front fins and your eye with a circle in it. And then, yeah, it's got one fin back here. And they kind of got frowny faces. Oh, no, I undid that. Oh, undo. Oh, no, there you go. Kind of have frowny faces. No. Dang. I don't know how to erase it. Anyway, that's what a pike looks like. Okay, so it says it can accelerate from rest with a speed. Oh, okay. It's from rest to a speed of 4 meters per second in 0.11 seconds. All right, let's draw this as a motion diagram. Okay, so first you start at rest. T is equal to 0. And then you move forward a little bit, and then you move forward a little bit more, and then you go in super fast. So that's t is equal to 0.11. And the question is, what's the acceleration? So again, just like we did up here, it's delta v over delta t. So v final minus v initial divided by delta t. So that's 4 minus 0 divided by 0.11. Wow, that's 36.4 meters per second squared. Incidentally, that's 3.7 G if you like rockets and stuff. That's pretty fast. Okay, how far does the pike move during the strike? That's actually a pretty good question. So to illustrate on this diagram, they're asking us for this distance here. And the tricky business is, we've got a couple velocity pieces of information. You know that the initial velocity is 0, and then you know what the final velocity is. So you have some velocity information, but the velocity is always changing. So instead what we're going to do is we're going to put these into the constant acceleration equations. And so, just like with the watermelon, the first thing I have to do is I have to set an origin, and I have to decide which way is positive. This allows me to write down these acceleration numbers and stuff with signs, and it lets me interpret the answers I get. All right, so the initial position is 0. the initial velocity is 0, and the acceleration is 36.4. I'm going to put these into the equations. X is equal to x0 plus v0t plus 1/2 at squared. So that's 0 plus 0t plus 1/2 times 36.4 times t squared. I'll clean this up a little bit. Looks like that. I know the time when I'm done accelerating, so I'm going to plug that into this. 18.2 times 0.11 squared, and that tells me 0.22 meters. It didn't go very far, but you know, they live in like murky rivers and lakes and stuff, so they don't have to go very far to bite the thing in front of them. I'm a bug. It's too dark to see, so I'm just gonna float around inside waiting for a swimmer to come by so I can bite them in the leg. And the pike's like, nope. Yomp. Any questions? Okay. Well, I guess let's move on to question 33. We're burning through the questions super fast today. Question 33. 33 goes like this. A driver has reaction time 0.5 seconds, and the maximum deceleration of her car is 6 meters per second squared. She's driving at 20 meters per second when suddenly she sees an obstacle in the road 50 meters in front of her. Can she stop the car in time to avoid the collision? This is a fun question. Okay, so there's a right way and a wrong way to do this. Essentially, here's the thing. Let's start by drawing a picture. Drawing a picture always makes things more fun. Okay, so there's a deer in the road. And here's her car. All right, so it's got some velocity. Draw it down here as well so I can draw all over it. I wonder if there's a cut and paste thing in this. I don't know. Okay, down here, how about if there's a rabbit in the road? And then here's her car. Oh, it's got a big back tire. 20 meters per second. 20 meters per second. Okay, so they give us a deceleration. Okay, so they go, oh, a person has a deceleration, and so what they're going to do is they see the thing and they immediately start slowing down. Moment later, slower. Another moment later, even slower. Another moment later, even slower, until you come to a stop. And then the question is, how far do you go before you stop? So let's assign a coordinate system to this. I'll say this is x is equal to 0. I'll say this direction is increasing. So the bunny here should be at, let's see, what did they say, 50 meters. I'll do it here too, just to be consistent. X is equal to 0, increasing, and that's at 50. So these questions say, how long does it take to stop? And where do you end up? What's your final position? If your final position after you brake is past this point, then it means that you've hit the bunny. So, you know what the acceleration is. They give you the acceleration. They say the acceleration It's a deceleration, which means that it's pointing in the opposite direction of your velocity. And it's 6 meters per second squared. Your initial position is going to be 0. Your initial velocity is 20. And your acceleration is -6. Why is it -6? I'm comparing the direction of the acceleration to the direction it's increasing. And then I plug these into some equations. So there's position, I should write zeros. Cool. 0 plus 0t plus -6 over 2 t squared. V is equal to 20 minus 6t. Okay, so how do we do this question? The deal is that this question's asking, when do we brake? When and where do we stop? This is a question that describes the motion. They're giving us a motional cue, not an emotional cue, a cue about motion. So they're saying we're looking for when v is equal to 0. How do we solve for that? You can use this equation here. 0 is equal to 20 minus 6t. So t is equal to 3.33 seconds. And you can plug that into this equation. So the final position, stop. The final position is going to be -3 times all squared. Wait, hold on. What did I just do? The initial velocity is not 0. The initial velocity is 20. Okay. So x is equal to 20 times 3.33 minus 3 times 3.33 all squared. Plug all that into each other. 20 times 3.33 minus 3 times 3.33 all squared. Really? Try that again. Wow. All right. So what we just calculated isn't the displacement, it's the final position. So we can interpret this final position in terms of displacement and say that that's how far the car took to stop. Well in front of the bunny, and everything's okay. So you'll note that in this question, they gave us information about distances, displacements, and in assigning a coordinate system, like we did, we were able to parse positional information into, so by parse I mean interpret, we were able to interpret this positional information in terms of displacement, how far you go. You had 50 meters to stop, you only stopped in 33.3. Okay, but I don't know if I mentioned it before, this is the wrong way to do it. It doesn't work. Why is it the wrong way to do it? Well, we missed a clue when we started this. The question starts, a driver has reaction time 0.5 seconds. Why would they tell us that? They tell us that because you don't brake right after immediately the moment you see a thing. You're gonna brake. It's gonna take a little bit of time to recognize that there's trouble. So for the first little bit of time, you're going to move with a constant velocity. And only after t is equal to 0.5 seconds, I guess. Only after that are you going to start slowing down. Okay. So for the first bit, you're moving with constant velocity. And then for the second, you're going to decelerate. So the question is, where's this final stopping point? Well, good news. We've already done half the calculation. Even if this calculation, even the way we did this over here is wrong, it has some aspects that are right to it. So for instance, we know that the distance between where you start stopping, where you put on your brakes that time, and this time, we know that that's going to be 33.3 meters. So then the question is, when do you start pressing the brakes? You start pressing the brakes 20 seconds after you notice that that there's a deer in front of you. So for the first part, you're moving with constant acceleration. That's v times t plus x0. It took you 0.5 seconds to recognize that there was a problem, and that puts you at position 10 meters. So we know that this distance here is 10 meters. You know that this distance here is 33 meters. So this final position is going to be at x is equal to 43.3 meters, which is still well short of the 50 meters. So you're okay. You start before you end up at a place before you've hit this deer. So that's fun, right? Do you have fun? I had fun. Let's move to the next question. Next question is question 34. All right. Question 34 goes like this. Chameleons catch insects with their tongues. So do politicians. Oh, wait. They should their prey. Anyway, forgot what I said. Chameleons catch insects with their tongues, which they can rapidly extend to great lengths. In a typical strike, the chameleon's tongue accelerates 250 meters per second squared during 20 milliseconds. Then travels at a constant speed for another 30 milliseconds. During this total time of 50 milliseconds, that's 1/20th of a second, how far does the tongue reach? Okay, so to start this question, you obviously have to draw a chameleon. What do they look like? Well, they always live on branches, so let's draw it by drawing the branch. Okay. And then they've got feet. And their feet are all grippy and weird. Grippy and weird. And their bodies are pretty lizardy as far as these things go. I think they're kind of hunchbacked. And I'm not sure why, but I think they have swirly tails. Their faces, on the other hand, have these super weird eyes. Chameleon eyes. Let's see if I can draw them properly. They have these they're independently chameleons can move their eyes independently of one another, so that's super weird. And also the main thing about chameleons is they change color depending on what's surrounding them to get better camouflage. So if they're in a forest of red flowers here, they're going to get kind of a red flower pattern to them. Okay, and here's what their tongues look like. They look like spirals. I don't actually know if they spiral like that, but whatever. There's room for whimsy in this world, that's what I say. Okay, so let's talk about the motion. Oh man, that bump in there is killing me. Let's try this again. Yeah, that's straight. Okay. So I'm going to draw a motion diagram for the tip of the tongue. Right there. It's going to travel. It's going to accelerate and move. So at the start, it's got... Oh, wait, let me... Oh, that's not too bad. At the start, it's going to move very slowly. And then it's going to pick up speed and travel faster and faster and faster. And then it's going to move at constant velocity. So, in other words, we're going to divide this motion into two parts. V is equal to constant, and acceleration is equal to constant. Okay, so they've given us the acceleration and not much else. They've given us some time stuff here. Maybe I should note that. See, t is equal to 0 is when you're over here. It's going to accelerate for 20 milliseconds. So this point here is 20 milliseconds. 0.002 seconds. And then it's going to be over here at t is equal to 0.00. Oh, geez. Five milliseconds. Okay. So the deal is that our answer for the first part is going to help determine how we start the second part of the question. But we're going to analyze each of these individually. That said, even though we're going to analyze them individually, that doesn't mean that we need different coordinate systems. Let's set this as my coordinate system. I'll set this point here at x is equal to 0. I'll set this point to be increasing to the right because I'm not a sociopath. I don't know where this point is, though. X equals question mark. So let's start by using the constant acceleration equations. What have we got? Their initial position is 0. The initial velocity... Oh, what? Sorry. The initial velocity is 0. And the acceleration is going to be 250 meters per second squared. That means the position as a function of time is going to be 0 plus 0t plus a over 2t squared. I'm just going to write this part of it. So this is 250 divided by 2 times time squared, and the velocity is 0 plus 250 times time. All right. So the question here is, where is this point and how fast are we traveling at it? So the nice thing about it is we know exactly when this point is. So plug this number in. That's at position 125 times 0.002 all squared, which gives us and V is equal to 250 times sure don't go very far. Well, that's positively lethargic. Am I doing this right? Oh, you know what? I've got the order of magnitude wrong here in this question. The question doesn't say it accelerates for 2 milliseconds. says it's going for 20 milliseconds. So use my correction color. Actually, you know what? Let's get rid of all this junk. All right. So this is at t is equal to 0.05. No. t.002. And this point over here is at t is equal to 0.05. Okay. So what that's going to do is it's going to modify these a little bit. Hold on. 125 times 0.2 times 0.2. So this is 5 meters. Really? 0.02 times 0.02. It's 125. No, it's not 5 meters. It's 5 centimeters. And this other one is 250 times 0.02. 5 meters per second. All right, that's a little bit better. So we know that at this moment, its velocity is going to be at a constant 5 meters per second. And we know that it starts from 0.05 meters. There's one of two ways of doing this. One of them is that we could find the displacement, delta x, because we know what its velocity is and we know how much time it takes. In that case, it's 0.15 meters. And that means the final position is going to be at 0.2 meters. Another thing we could do is we could make our own position versus time equation. This one's easier. So instead of doing another position versus time, I just knew what delta t was. I knew it was a constant velocity motion, so I could figure out what this displacement was. Okay, so I know the final position is at 0.2, and the question goes, how far does the tongue reach? And the answer is 20 centimeters. 20 centimeters, is that a long distance? That's pretty long for a little lizard, I guess. I just thought they'd be longer, but I guess, you know, if there's a bug on a leaf over here. I wonder how chameleons aim if they don't have binocular vision. I mean, they've got binocular vision, but not stereo vision. They can't depth things. Maybe they can. Maybe that's the trick to chameleons. I thought it was changing color, but it just goes to show. All right, last question of the day, 36. A light rail train is going from one station to the next on a straight section of track, accelerates from rest at 1.1 meters per second squared for 20 seconds. It then proceeds at constant speed for 110 meters, 1,100 meters, before slowing down until it stops at the station. How much time does it take to go between stations, and what's the distance between stations? This is a fun question. Okay. So, here's the idea. Here's station 1. Here's station 2. You don't know much about their distance, but you do know that a train goes between them. And you know how the train is moving. I'll draw it in purple, I guess. First, the train starts off at rest, and then it speeds up, until a certain time. And then it travels with constant velocity. That's not constant velocity. Count the things. Why am I on graph paper if I'm not going to count the things? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So it moves with constant velocity for a little while, and then it starts to brake. So it's going to start slowing down until it stops. So the acceleration on this part goes like that. There's no acceleration in this part, and the acceleration in this part goes like that. I know the magnitudes of accelerations. So for instance, I know it goes here 20 seconds. But I don't know, and I know that this distance here is 110 meters. But I don't know what this distance is, d2, and I don't know what this distance is, d1. I know how long it takes to reach this point in time, but I don't know how long it takes to go from here to here, and I don't know how long it takes to go from here to here. That information, I need to know how fast it's traveling at this time, because this is a constant velocity, so I could use that to figure out how much time has passed. And this one, it slows down from our initial velocity, and so if I knew how fast it was traveling initially, I could figure out how long it would take to brake and how far it would take to brake. So let's do the problem. Let's see. Okay, so the first thing I have to do is assign a coordinate system. I'm not going to be fancy here. X is equal to 0 here. That way increasing x. Okay. So with that in mind, your initial position is going to be 0. Your initial velocity is going to be 0. And your acceleration points in the direction of increasing. So the acceleration is going to be plus 1.1. So I plug this into position versus time equations. So it's going to be 0 plus 0t plus 1/2 at squared. So it's going to be 1.1 divided by 2 times time squared. And your velocity is going to be 0 plus at. So it's going to be 1.1 times t. So I know you accelerate for 20 seconds. So I can figure out what your position is then. 1 over 2 times 20 squared is equal to 220 meters. And your velocity is going to be 1.1 times 20. So it's going to be 22 meters per second. Cool. So that means that for this stretch, you're moving at 22 meters per second, and it also means that I know that this value here is equal to 220 meters. So this particular question has two parts. It might be easier in this case just to keep going with what we know. So I don't know the final time here, and I don't know how much time it takes to go from this point to this point, but I do know the distance between them, and I know the velocity because it's a constant velocity, and so delta x is equal to v delta t, so that's 20, no, not 22 there, it's 100. 110 is equal to 22 times delta t, and delta t is equal to 5 seconds. Really? Let's try it again. 110 divided by 22. I guess that makes sense. So it takes 5 seconds to go from here to here. So the time here is 20 seconds. And the time here is 25 seconds. Okay. Now it's for the fun part. If you're good at math, it's actually pretty easy to take initial conditions and plug them in. Even if the initial conditions aren't at time t is equal to 0. But, you know, I'm not entirely certain that if I do that, you'll have an easy time of it. So instead, I'm going to reset time. I'm going to reset my clock here. Call this the new t is equal to 0. Okay? So the initial position at this is 220 plus 110. It's at 330 meters. The initial velocity is going to be 22 meters per second. The acceleration goes backwards, and it's minus 2.2 meters per second squared. So I'm just going to plug these guys into our time coordinate, into our position versus time motion. So this is 330 plus 220 times t prime plus minus 2.2 divided by 2 t prime squared. V is equal to 22 minus 2.2 t prime squared. So now I can use these equations to interpret where it stops and also where the final point is. So let's figure out where it stops. It's going to stop at, so v is equal to 0, 22 minus 2.2 t prime. Wait, there shouldn't be a squared there. Okay. So t prime is equal to 10 seconds. It takes 10 seconds to come to a stop. So that means it stops at 35 seconds. These train stations aren't very far apart. Wait, no, they're pretty far apart. Maybe they're just going gangbusters. And then so the final position is 330 plus 22 times 10 minus 1.1 times 10 squared. Do that calculation. 330 plus 22 minus 1.1 times 10 times 10. So this isn't the displacement. FYI, the thing we just calculated, that's not this value. The thing we've calculated is the final position coordinate. There. So the answer to A is how far are the stations apart? 440 meters. B, how much time does it take to go between the stations? 35 seconds. Ta-da! Oh, there is no visual for this question. Which question are you talking about? Is that the stream says it's working? Sorry, somebody just wrote there is no visual for this question, and they wrote it about a minute ago. Oh, are you still getting video? Hold on. Oh gosh. Oh no! Thank you for telling me. Let's see. Maybe I'll have to do this again. Yeah, there we go. Okay, so you should be able to see it now. Oh, dude, that's so sad. Okay. Yeah, so sometimes the software that I'm using, after pretty much exactly an hour by its clock, it'll shut off. It's trying to get in time. All right, what does this say? The last one, yes. Thank you, Sadidi. Let me just narrate what this picture says. I'll do some erasing. Because you've already heard the narration, presumably. You just didn't see the video. So... I'll narrate how to solve it visually, but I've already done the math, so you can go through the math on your own. It's all written below here. Okay. So the way to start these questions is to draw a motion diagram. And there's three aspects to this thing's motion. First, it starts from v is equal to 0, and then it speeds up faster, faster, faster. And then, after, I guess, 20 seconds, it moves at constant velocity. You see constant velocity? The distance between these is increasing because it's accelerating, and then constant displacement for each of these times. And then, at t is equal to question mark, it starts to slow down. Okay. And we don't know a variety of things about this particular question, although we do know some things. So for instance, we know that the distance between this part, when it's got a constant acceleration, v is equal to constant, a constant velocity, we know that that's 110 meters. You don't know how far this is, though. And you don't know how far this is. I'll call that D2. So you don't know a lot of things. You don't know what time you reach the end at either. But this gives us a good place to start, and also we've kind of cut up our page in an interesting way. So what you need to do is, you know the acceleration here is in this direction, and you know how big the acceleration is. And you know in this part the acceleration's in that direction, and you know how big it is there. It's 1.1 on this side, and it's 2.2 over here. So starting at t is equal to 0, the first thing I need to do is assign a reference frame of coordinate system. So I do that, and I'm not going to get too weird. I'll just say that this is at x equals 0. And then I'll say that this direction is increasing. So then I'm going to use the equations for the different types of motion to parse this out. So on the first part here, I'm going to use what I know. Its initial position is 0. Its initial velocity is 0. They give me the acceleration. I'm going to plug them into the constant acceleration equations and then solve them to figure out, because I know exactly how much time it took, I can figure out where the final position is. So I can figure out that that is at 220 meters, and I can figure out the final velocity. Oh no, that's not what I want. I can figure out that this velocity here is 22 meters per second. Next, I know how far it moves under constant velocity. That's this branch, but I don't know what time it reaches the end. So since I know its displacement and its velocity, I can figure out how much time it spent moving. And so 5 seconds. So that means it reaches this point 5 seconds after it reached this point. So it's going to reach here at 25 seconds. So how do we do the last part? Well, it's moved at constant velocity through all this branch, and so it's going to enter this last part moving at 22 meters per second. It's actually a little bit tricky to break down. Wait, is it frozen again? No, it hasn't frozen again. It's a little bit tricky to break down how to start this to write another set of equations, position versus time, describing the motion from this point on. So starting at this here, I'm going to say t is equal to 0. T prime is equal to 0. I'm going to start my stopwatch at that time. So starting from that time coordinate, I know my initial position here is 3. So here's the position versus time for here's the position versus time in terms of t prime, which is the time starting when I reach here, and then I solve this for when it stops. I know it stops, v is equal to 0 over here, so I move. Hey move. Hey move. So I solve it for v is equal to 0. That tells me how much time it took to stop. Okay. And it also tells me, because I used this is my initial position, x is equal to 330 is my initial position, these don't describe displacement. They describe my position on the track. So at this time, t prime is equal to 10. My final position is 440 meters, so I know that this final position is at 440, and I can figure out, I know that it's taken 10 seconds to go from here to here, so the final time is 35 seconds. And that's how to do it. And that's it for the thingy today. Have a nice day, everybody. I don't know, I guess I can look to see if anybody has a question. Thank you for pointing out when you couldn't see it. That was really helpful. So any questions? Please go ahead and mention if you have any questions. Oops. Is it being such a... Alright, nobody's asked any questions, so I'm gonna take off. Have a nice day, everybody. Whoa, what's that thing? Who knows? This thing, I tell you. Stop streaming.